Hello everyone. Today we're going to be learning some more Algebra 1. And we're going to have two goals today. One is we're going to find square roots. And that doesn't mean that when you go in your backyard you see a tree and it has roots running that you look for square ones instead of circular ones. Does not mean that. We'll learn what that means today if you don't already know. And the second thing is we're going to classify and order real numbers. Not fake numbers, but real numbers. And we'll see what that means today as well. We're going to have a lot of definitions today, so hope you can keep up. If you can't, you can always pause and rewind. There's nothing wrong with that. And we're going to make sure we break down things real simple so that way we can do this. Alright, so let's go ahead and dive on in and let's do some definitions. Let's look at square root. Well, we know it doesn't have to do with trees, so what is a square root? So this is one of two equal factors of a number. You're like, that sounds like Greek to me. Well, so if you multiply two numbers together that are the same number, you come up with another number, okay? So it's basically the reverse order of that. You're trying to find out which two numbers are multiplied against each other to come up with that number. And we'll see some examples. It maybe make more sense when we see some examples. But let's cover another definition here. Perfect square. So is that talking about a square that has sides all equal? Well, that's just a normal square. Let's see what this means. This is a number whose square root is a rational number. Okay. Anybody remember what a rational number is? So those are numbers that can be expressed as either terminating or repeating decimals, or they can be like a fraction where the denominator is not equal to 0. And in the fraction you have to have integers. Okay. Let's talk about another definition here. Radical sign. Whoa. What is that? Well, that's this thing here. That looks rad. Yeah, it's radical. Okay, so what does this do? Well, it's used to indicate a non-negative or principal square root of the expression. So earlier we were talking about square roots. And this is what you're going to use when you show that you're trying to get the square root of something, okay? So you're going to put the numbers underneath this little house looking thing. You're going to put it inside here where x is, okay? Alright, let's look at an example. Alright, so we want to find the square root, okay? So we have minus the square root symbol of 9, oof, that was a terrible looking 9, of 9 over 49, okay? So we're going to carry this negative sign, and let's break this into two parts. Square root of 9 and square root of 49. Okay, we can do that. Rather than doing it all together, we can do it one piece at a time. So what times itself is equal to 9? 3 times 3 is 9, so that would be 3. What's times itself is 49? That would be 7. So that's our answer. It's minus 3 over 7. Great job. Let's look at another one. Let's say that we have plus or minus the square root of 0.144. Okay? So what times itself is 144? 12 times 12 is 144. But we have this decimal place, right? So let's carry over this sign. And inside of here, we're going to do 0.12. Oh, without the square root symbol. Okay? So 0.12 times 0.12 is 0.144. So that's the answer. Alright. So let's talk about a couple definitions here. Let's remind ourselves, because we've covered this already, but a rational number. So that way we understand what an irrational number is. So a rational number, it's rational, right? It's numbers that can be expressed as terminating or repeating decimals, or in the form A over B, where A and B are integers. And one more stipulation, B is not equal to 0, because we do not want infinity. Although it's probably a pretty nice card to draw. Alright, so let's talk about irrational numbers. Okay, this is the opposite of rational. So basically, we can repeat the same definition, but we want to say numbers that, and I'll put this in red, cannot be expressed ... because it's the same definition. Okay, so it's the opposite. Alright, so instead of terminating, it's not terminating. Instead of repeating decimals, it's not repeating decimals. Or if it's in the form of A over B, A and B are not integers. Or something like that, okay? So let's look at a little diagram. Okay, we're going to draw a box. Box, box. Box, box. Alright. And we are going to draw inside this box some more lines. Okay. Alright. So here we're going to say real numbers. Okay. And everything included this box is a real number. We can have rational numbers, and we can have irrational numbers. Okay, so those are subsets of real numbers. Let's look at some subsets of rational numbers. We can have integers. We can have whole numbers. And we can have natural numbers. Okay? So integers are whole numbers and natural numbers. Whole numbers are natural numbers. Natural numbers are whole numbers are integers. And integers are rational numbers are real numbers. Irrational numbers are real numbers. So it's a nice little diagram to kind of see what we're talking about. All right, let's look at another example here. And what we want to do is we want to name the set or sets of numbers to which each real, does not look like real number belongs. Okay, let's look at A here. We want to look at 1/3. All right, so 1 and 3 are integers. Okay. And if we put 1/3 in decimal place, it'd be a repeating decimal. So it is a repeating decimal. Which is a rational number. Okay. Let's look at another one. Let's look at the square root of 49, which is equal to 7. So this is a natural number, right? This is a whole number. And so therefore it is also an integer, and if it's an integer, then it is a rational number. Okay? This is how we classify this. All right, let's look at another example here. All right. So let's look at the square root of 56. What is this equal to? If I use my calculator and I take the square root of 56, I get 7.48331 and a whole bunch of other numbers. So this is not a repeating decimal or a terminating decimal. Okay, which is an irrational number, right? Based on our definition that we had earlier. Great job. All right, let's look at another one here. Let's have minus 12/3, which is equal to minus 4. Okay, so minus 4 is an integer, which is a, you tell me. If you said rational number, that is correct. It is also a rational number. And we'll try to write a little bit clearer here. Okay, great job. All right, let's talk about another definition here. We have the completeness property. Okay, this is when each point on the number line corresponds to exactly one real number. Okay, so let's look at an example here. Example 3, and let's do part A here. Let's do when x is greater than -1. All right. So let's draw the number line. And let's start over here with 0. And let's do a -1, -2, and let's do a 1 and a 2. Okay, how do we draw this? Now I'm going to use different colors here to help show where this is, okay? So we do not want when x is equal to -1, it's only greater than -1. So the way that we designate that is we're going to draw a circle on -1. But it's going to be an open circle. It's not going to be a solid circle. We're not going to fill in that circle. Okay? Because we do not want to include 1. We just want to include everything that's greater than -1. So if it's greater, it should be to the right. So we will draw green on top of our red here to show that. Okay? So that's when x is greater than -1. Let's look at another example. Let's do when z is less than or equal to 3.5. All right, let's draw another number line here. All right, let's have a 0, -1, -2, -3, -4. We have a 1, we have a 2, we have a 3, and we have a 4. All right, so we need to find 3.5. So 3.5 would be halfway between 3 and 4 because it's a positive 3.5, right? So it's on the right of 0. Now this says less than or equal to 3.5. So we need to fill in this circle here. Yep. So it's a solid circle then. All right, now we want less than 3.5 and equal to 3.5. So we need to go to the left. So we'll draw a green line here and show that that is going to the left. Okay, great job. So I have one more definition for you. So just hang in there just a little bit longer. So this definition is rational, if I can write, rational approximation. All right. So this is when a rational number that is close to, but not equal to, the value of the irrational number. Okay, it's close, but it's not quite there. So this is a rational approximation. Let's look at an example. Example 4 here. All right. So there's only multiple parts here, so what we want to do is we want to place less than, greater than, or equal to make each sentence true. Okay? We will make each one true. All right. A. We got square root of 12, and we have 2.4 with 4 repeating. So we want to put in between these two, we want to put whether it's less than, greater than, or equal to. How do we figure this out? Well, let's think about this. So let's think about 12 and a number that's less than 12 that is the square of something else. Okay, let's think about 10, 11 is not a square, 10 is not a square, 3 is a square, 3 times 3 is 9. So let's do 9. We know that that is less than 12. Let's pick something bigger than 12. 13 is not a square, 14 is not a square, 15, 16 is a square because square root of 16 is 4. Alright, so we know that this is true, right? So if we know that this is true, we also know that if we add just square root symbols over each one, that this is also true. Well, if we know that that's true, then we know that 3 is less than square root of 12, and that 4 is greater than the square root of 12. Well, we know that 2.4 is actually less than 3, right? So then we know that square root of 12 is greater than 2.4 because if it's greater than 3, 3 is greater than 2.4. So then we know that it should be this. Okay? Let's look at another example. Alright, so we have 7.2 repeating, and we have square root of 40. Alright, well 40 is getting to be a pretty big number. So we're just going to use our calculator, and square root of 40 is equal to 6.324 a bunch of numbers. Okay, so is 6.3 greater than or less than 7.2? It's less. 6 is less than 7, right? So then 7.2 repeating is greater than square root of 40. Great job. All right, let's look at another example here. Okay, we want to write 1.63 with the 6.3 repeating, negative square root of 6, 7 over 2, and 43 over minus 10 in order from least to greatest. Alright, so we want to write from the smallest to the largest, from least to greatest. Okay, so we have a positive 1.63 repeating. Okay, we have a minus square root of 6. So we know minus is less than anything positive, and that's equal to minus 2.449 bunch of numbers. Alright, and we know that 7 over 2 is equal to 3.5, so we know that that is greater than 1 point something, and of course bigger than anything negative because it's positive. And then we know that 40, oh that's not a 4, 43 over minus 10 is the same as minus 4.3. Okay, so there we got two minuses and two plus. So we know that one of the minuses has to be smaller. So which one's smaller, minus 2.449 something or minus 4.3? Remember, on our number line, the smaller stuff is to the left. Okay, so minus 2 is smaller than minus 1. So therefore, minus 4.3 would be the smallest. Okay, let's list this the original way. So we'll say minus 43 over 10. So then the next minus we know is minus square root of 6. All right, now which positive number is smaller, 1 point something or 3 point something? That's right. It'd be 1.63 with repeating 6.3, and then 7 over 2. All right, so that's from least to greatest. Great job. All right, let's look at one problem here. And let's write it out. The time it takes for a falling object to travel a certain distance d is given by the equation t is equal to the square root of d over 16. That's a bad looking 16. Let's try her again. Where t is in seconds and d is in feet. All right, so what's the question? Let's write that in a different color. If Mavia dropped a ball from 64 feet above the ground, how long would it take for the ball to reach the ground? Okay. So Mavia is somewhere, 60 feet up, 64 feet in the air. Maybe he's in a high-rise building looking out a window with a ball. And there's no one below. We don't want anybody to get hurt, of course. And he's going to drop this ball and just let gravity take over. Gravity? What is that? Well, have you ever tripped and you hit the ground? Why don't you float? Because there's something bringing you down. That's gravity. Okay? It'll bring you down to earth. All right. More than one way. So let's solve this problem. We want to plug in for d the distance in feet, 64 over 16. Okay, now let's break this down. Square root of 64, that's a bad looking 4, over the square root of 16. All right, what times itself is 64? 8 times 8 is 64, so this will be 8. And then what times itself is 16? 4 times 4 is 16. So this will be 8 over 4, which is equal to 2 seconds. All right, so it takes 2 seconds for that ball to drop from 64 feet down to the ground. 2 seconds. It's not long at all. All right, that's all we have for today. I really appreciate your all's time, and hope you learned something. If you have any questions or anything, I'll try to address it in the comment field. And if you want to see more of this, let me know. If you'd like to see another topic, let me know, and we'll see if we can work it in somewhere. And if you haven't subscribed already, please subscribe and like the video. I'll see you all later. This is MP.